For over a century, electrical grids were built on a simple, one-way physical principle. Power flowed strictly outward from central substations down, through distribution lines to the end consumer. This legacy infrastructure was engineered entirely around that top-down model. Transformers, protective relays, and cables were sized assuming power would never travel in reverse. But today, we are adding massive distributed generation, or DG units, to the extreme ends of these older networks, like solar arrays and microhydro plants. There is a common assumption that because these are clean energy sources, connecting them to the grid is as simple as plugging a USB drive into a computer. Physics dictates otherwise. When a solar plant injects a megawatt of power at the feeder's end, it collides with the substation's natural flow, creating reverse flows. This collision spikes localized voltage, distorts sine waves, and blinds standard overcurrent relays. To prevent systemic failure, regulators enforce strict mathematical boundaries. In Indonesia, this is governed by the Grid Code, Peraturan Menteri ESDM number 20 of 2020. Interconnecting distributed generation requires solving a multivariable physics problem at a specific engineered interface, the point of common coupling. To see how these physics break the grid, we have to look exactly where a 1 megawatt generator ties into the far end of a typical 20 kilovolt distribution feeder. By injecting large amounts of active and reactive power into the resistance of the cables, the generator forces energy upstream. This localized pressure stacks up, forcing the voltage to rise. We can estimate this change in voltage, delta V, using the line's resistance and reactance. This equation shows how the injected active power, P, and reactive power, Q, directly drive the voltage rise. If we run the numbers for a 1 megawatt injection on a standard line, the local voltage is pushed from its baseline of 20 kilovolts up to 21.2 kilovolts. The grid code mandates a strict boundary for continuous operation. Voltage must remain below a ceiling of plus 5%, which is exactly 21 kilovolts. Our calculated 21.2 kilovolts physically breaks through that maximum allowable limit. To bring that voltage back into range, the inverter must manipulate the Q variable in our equation. By using volt-var control to absorb reactive power, the inverter creates a negative Q value, which mathematically pulls the local voltage back down below the 21 kilovolt safety ceiling. The threat goes beyond macro power flow. We also have to examine the microscopic quality of the electricity itself. Solar and wind plants rely on inverters, which use rapid power electronic switching to convert DC into AC. This switching process inherently injects high-frequency distortions, electrical dirt, into the clean 50 Hz sine wave. This is measured as total harmonic distortion. The grid code mandates that this distortion remain below 5% to prevent severe interference with other consumers on the line. There is a secondary and far more destructive power quality threat: direct current injection. If an inverter is poorly calibrated, it can accidentally leak continuous direct current onto the alternating current grid. When this leaked DC reaches the utility's step-up transformers, it causes immediate magnetic saturation within the iron cores. That saturation leads to extreme overheating, and ultimately it causes the catastrophic physical failure of the utility's entire transformer. A distributed generator must guarantee pristine power quality. If it doesn't, the inverter becomes an active hazard that will physically destroy the utility hardware it connects to. Even if a generator connects safely, it must survive the grid's daily reality. Consider a transient fault, like a lightning strike that drops the network voltage to 0.5 per unit for a fraction of a second. The legacy programming of early grid-tied inverters was to immediately trip offline during any voltage dip to protect their internal electronics. But if thousands of distributed solar arrays trip simultaneously during a minor lightning strike, the grid loses a massive portion of its generation capacity in milliseconds. This sudden loss of generation forces the grid frequency to plummet, dragging the entire distribution network into a blackout. To prevent this cascading failure, modern regulations mandate a specific performance standard known as low voltage ride-through, or LVRT. This curve maps grid voltage on the vertical axis against time on the horizontal. In the bottom left corner is the allowed to trip zone, representing severe, unrecoverable faults where the inverter is permitted to disconnect. But the vast majority of the graph is the mandatory stay connected zone. If we map our lightning strike scenario,
a voltage drop to 0.5 for 0.16 seconds, it lands squarely inside this mandatory zone. To maintain stability, modern DGs are legally obligated to act as shock absorbers. The LVRT curve requires them to hold the line and support the grid through the turbulence, rather than disconnecting at the first sign of trouble. All of these physical vulnerabilities, voltage rise, power quality, and write-through, must be managed at the physical boundary separating the private generator from the utility network, the point of common coupling. The PCC functions as a high-speed protective firewall, enforcing the grid code's logic at the millisecond level. A properly engineered interconnection begins with the 20 kilovolt distribution line, a step-up transformer, and a main circuit breaker. To prevent the voltage rise issues we calculated earlier, we install ANSI relays 27 and 59 to monitor for under and over voltage conditions. To ensure the inverter stays perfectly locked to the grid's 50 Hz rhythm, we add the 81 over and under frequency relays. And to enforce the contractual limits on exported power flow, we install the ANSI 32 reverse power relay. This interlocked array of relays forms an automated system that will instantly sever the connection if the generator violates any physical grid parameters. There is one final, non-negotiable protection mechanism required at the point of common coupling: anti-islanding. Consider a critical scenario. A major fault knocks out the primary 20 kilovolt substation, cutting all power to the distribution feeder. Without anti-islanding protection, the local solar array might attempt to keep the neighborhood running, unknowingly backfeeding 20 kilovolts of power into a line that should be dead. This creates a lethal hazard for utility linemen who are dispatched to repair what they assume is a safely de-energized cable. The anti-islanding relay actively detects the loss of the main grid's 50 Hz reference pulse and triggers a mandatory, life-saving trip of the generator. Load flow studies, short circuit analysis, and strict grid codes provide the fundamental mathematical proof required to build a safe, bidirectional modern power grid.